YT channel. Okay, I'll be able to discuss at this moment in time. Hello again, I was, gosh, I'm coming live and then I was disconnected in a quick second, and then after that, okay, I'm reconnected again. What's happening to my mobile phone and what's happening to the network provider at this point in time? Okay, going back to thermochemistry, but this time I'm gonna be focusing for the phase changes. Okay, phase changes of enthalpy or heat energy, heat changes or phase changes. Okay, heat energy being transferred from one point to another point, something like that in a certain path. Okay, that is enthalpy change, right? But here we will be able to discuss the enthalpy change of phases, meaning solid, liquid, and gas, three phases of matter. So let's forget a little bit with the chemical reactions. Okay, the chemical reactions are focusing on the breakdown of reactants to produce products, right? But in here, phase changes enthalpy main topic. Okay, but still this is under thermochemistry. Okay, something like that. Now I will get my table of the data of enthalpy change of formation at standard conditions at 298 Kelvin and at also 1 atmosphere pressure. Let's check. Okay, because I kept that in my bag instead of my bag. I don't know if it is lost. I think so. I think it's here. Oh my gosh. Okay, so because there are times class that we don't have, there are times if we face an examination, especially physical, chemical, and response coverage, or science coverage in general, okay, sometimes they don't put or they don't give the enthalpy change of formation of a certain elements, compounds, inorganic liquids, organic liquids, or any enthalpy change formation of various substances. Okay, then we will be the one to obtain that values in, for example, in a chemistry textbooks or in a Paris Chemical Engineer's Handbook, because we have that also in our handbook. Okay, and then in physics book also sometimes, not really sometimes, all sciences books have really tables for that, especially physical and chemical data. Okay, that's really injected in the appendix, somewhere in the last part or sometimes in the front page. Okay, just scan and go over your books if you have books, if you have books right now. Okay, or you can go also to the website if you love really online surfing regarding pure sciences, and you can have to also. Okay, anyway, the basic and principles are constant. It will never be changed unless there's a new introduction of scientific discovery or scientific contribution. Okay, oh my gosh, it's lost. Oh my gosh, where's my records of FLPO formation? Oh, talaga. Wait ha, this one. So, I will read. Examples, standard enthalpies of formation at 25 degrees Celsius. Thermochemical properties. Actually, this is called thermochemical properties, right? Because our topic is thermochemistry. Of selected substances at 298.15 Kelvin and 1 atmosphere. This one. Here, in organic substances, there's a lot. Okay. Oh my gosh. I will tell you something. Oh, really? 2, so many. 3, 4, 5, 6, 7, 8. Oh my gosh! 8 pages. 8 pages of standard enthalpy of formation of various products, specifically inorganic and organic substances. When we mean substances, it is either solid, liquid, or gas. So meaning substance is really a general term referring to three phases of matter. It could be solid, liquid, and gas. Okay, that is a substance. So sometimes we should be also be careful in using that term. Okay, that's general, right? So we always put solid substance, liquid substance, gaseous substance. But it is okay also to put substance only, but it will help the students to think, right? If it is gas, so in another way around, it will help us to think or to, to dig deeper. What is the substance all about? Okay, so it's okay also. It depends on the situation, really. Okay. Okay. So I closely examined this thermochemical properties. Okay, this thermochemical properties, guys, is very useful in physical chemistry and chemistry because this will really come out in the board examination. Okay, especially for physical and chemical coverage, right? This is not really so related to chemical engineering, but only sometimes, especially in the heat transfer unit operation. This will be used, heat transfer, transport phenomena. But what I'm talking to is that this exclusive topic will come out in physical chemistry or in chemistry, that those are belongs to physical and chemical coverage principles. Okay? Always like that. Physical and chemical principles. Okay? Or theories, subject, something like that. As I noticed here, class, the values of standard enthalpy formation of various inorganic and organic substances are really negative. Okay, so meaning to say pala, negative siya. Those are spontaneous. Okay, meaning because it has a negative value of delta H. So at 25 degrees Celsius and 298 Kelvin pala, most of the substances, whether it is inorganic and organic substances, will behave spontaneously. Okay, because it has a value of delta H negative. So, in natural process, this behaves in spontaneous manner. So, without putting energy, or you leave that here, just like that. For example, if I will put ethanol here and then water here, I will mix that together. So without adding anything, without adjusting the operating conditions or the parameters such as the volume, the density, the temperature, the pressure, automatically the reaction is spontaneous, meaning exothermic reaction. Okay, meaning originally and naturally. Okay, for this enthalpy values, negative. Since we know the relationship of enthalpy to free energy, the delta G, so most of the liquids pala siya at standard temperature and pressure are spontaneous. Okay? Something like that. Or behave in exothermic environment. Something like that. Okay, because delta H, enthalpy change, is directly proportional to the Gibbs free energy man siya. So if enthalpy is negative or less than 0, technically also the Gibbs free energy change of a particular substance is also negative. Something like that, okay? And the reverse will be the change in entropy. Okay, something like that. You get the point now? Okay? So if you will never touch that system, for example, okay, there's a higher entropy originally. Why I say that? Because they are going back and forth. Because that's spontaneous. It doesn't take energy to do that. Okay? It's really natural process. So meaning to say, the entropy naturally is very high. So it goes there, go back there, and it really goes back to original condition, and then produce a product, going back to the reactants without adding any external forces, energy and everything, chuba chum chu. So it holds true really that the entropy will be higher or greater than 0 when we have an enthalpy change or formation of various substances at standard temperature and pressure. something like that. Okay, so we should build, thorough foundations for this before we will be solving problems related to this three quantities in thermochemistry, particularly that gives free change of energy, the enthalpy change of the reaction, and also the entropy change of the system. So this three is very important, of course, in thermochemistry, which also touched specifically in thermodynamics. Okay? Something like that. Now, go back to our main topic. Okay, because this is very useful as I told you, right? Phase change, enthalpy formation of a phase change. Okay, so in this minor class, we need to focus not all the physical processes or whatever, we are only limiting to at least 5. Okay, because other phases changes will no longer apply this, enthalpy changes of formation theory, concepts, and principles, especially those belongs to the unit processes, right? For example, or unit operation like filtration, like this, sedimentation, flotation, leaching, like that. Okay, screening, something like that. So I think momentum transfer also. Okay, so it will not be applied there. Okay, it will be applied just, I think so, in unit operation, specifically focusing on heat transfer. Also, and a little bit with mass transfer also, because this is mass transfer is more on the phases also, the concentrations, referring to the concentrations of the substances. So it will be applied a little bit there, I think so, or maybe. Let's investigate. Oh, charot. Okay, I will get now a blank sheet of paper to take note what are those enthalpy formation that undergoes phase changes. So here we will be talking simply the 5. First, we need to talk evaporation. Evaporation is the same as a vaporization process. Okay, and then we reverse that. Okay, if we reverse that, that is sublimation. Oh, sorry, that is condensation pala. Okay, condense, because what I have in my brain cell, if it's going to be in a liquefied form, it will be condensed. So that is condensation. So I change immediately from sublimation to condensation. Gonna be things like that very quick, because you have now in your brain cells. Okay, so if you memorize that one, then if you are wrong, then you can automatically change because you have another concept in your brain cells, something like that. Okay. And then you need to find. So, okay, vaporization, the reverse will be the condensation. Okay, and then sublimation, what's all about? Sublimation. Okay, solid to ganon, gas. Okay, and the reverse, gas to solid, is very difficult. Is there any process that undergoes the reverse of sublimation from gas to solid? It's very difficult, right? How can we do that? Okay, but still there is a process known that in pure sciences. Okay, that's called deposition. Deposition, the reverse of sublimation. Meaning to say, a change from gas phase to solid phase without passing from liquid phase. Because sometimes also, others changes will pass pa siya through intermediate phase. Okay, for example, solid to gas. But before going to gas, this solid will change first to liquid. There's also like that situation. Okay, but in this case class, this deposition, or what we call as desublimation, okay, desublimation, Desublimation, okay, or deposition is the reverse of the sublimation, will not pass in liquid state. Automatically, okay, the gas will change directly to solid. Oh my gosh, amazing. It's very difficult, right? Okay, so that is sublimation, and then we have the deposition. And now we go also to the fusion. Fusion, what we mean by fusion? Okay, this is changes from solid to liquid. Okay, solid to liquid. So the example for this, there's a lot, right? For example, ice, liquid ice. or water in a solid phase. So the solid will change into the liquid, so that is fusion, or what we call also in another point of view, melting point, melting process. Okay, for example, if you are studying metallurgy, the alloying of some metals, something like that, right? Alloying, or you will be able to melt. Okay, so from solid, for example, solid magnesium or solid zinc, it will melt. So the change will, the phase will become liquid, something like that. So that is from solid, it changed to liquid, so that is fusion or melting. Oh, di ba? Ganun siya. So kung liquid to solid, ano naman siya? Liquid, a change from liquid to solid, what is that all about? Okay, that's why I told you, you will master all the processes. I told you over and over and over again, if you're studying chemical engineering, you have to memorize all the physical and chemical processes. Okay? Because this is very important in studying higher subjects in chemical engineering or even base chemistry, right? Especially in the unit processes, kinetics, like that. Okay, thermodynamics and physical chemistry or whatever, chuba chu. Okay, so as I told you, so if the reverse from solid to liquid is that is solidification. At least it's very easy to identify because okay, from liquid to solid, the product is solid, right? After the change, and then you will just add solidification. So it's very easy to memorize. Okay, because it's in the term alone. Okay, for example, blank is the change from from liquid to solid. Okay, automatic solidification. Okay, because the product is solid. Okay, like that. Okay, and then liquid, solid to liquid. So the reverse, it should be fusion or melting. So in this point in time, we will be dealing for that specific processes, and we need to apply the enthalpy change of the formation of the substances. Okay, and we will apply second law of thermodynamics. Okay, second law lang yun siya. Or we can also adopt the first law if we want to, but we will just focusing first the first law because the second law is more a little bit of shall I say complicated, not really that complicated, a little bit difficult compared to the first law. This is only my feeling. I don't know with other students or other chemical engineers out there or any engineers out there. This is only my feeling that this first law is more easier a little bit compared to the second law of thermodynamics. Okay? Sakto ba? Okay, I will get a blank sheet of paper now. Okay, let's go. Let's start with a very basic, with a pure substance, liquid water. Liquid water is very important for our daily lives. We will die without water because water comprises 75% of the planet Earth, and 75% also estimated in our body. Without water, we will die. So we will start with water. That's what we will say water is life. And there's no such chemical reactions most of the times in our physiological reactions in our body if there's no presence of water. The water is really important, okay, if we talk about chemical reactions. Okay, so we start with water in the first place. Okay, oh my gosh. So first, we need to talk. This is the very basic also of all, especially in making coffee, if we cook our food in our kitchen, something like that. So the process is always taking place is evaporation or vaporization. That's why we cook. Okay, if we observe the smoke and the vapor circulating or diffusing in the surrounding. So that means evaporation and vaporization took place. So don't be confused with the word vaporization and evaporation because it's just the same. Okay, evaporation is talking more on the general point of view. It's gonna be like that, and the vaporization is more specific because it will produce a vapor. The liquid will change into a gas, and then specifically that kind of gas is a vapor. Okay, specifically. That's why that is vaporization. That's why we have vapor pressure. Okay, we will never say gas pressure, but vapor pressure. Okay, that's the right term for that during evaporation process or vaporization process. And now let's apply that here. Okay, so first law lang. Okay, first law of thermodynamics. Okay. Okay, now let's review also ha, yung mga ganon, okay, Q. But before that, I must state also that the first law of thermodynamics is really focusing on the law of conservation of energy. Okay, that energy can neither be created nor can be destroyed, but it can only be transformed to various forms of energy. Okay, put that in your brain cells. Okay, like the basic concept of the first law of thermodynamics also, right? Okay, mura na siya because the second law is a little bit complicated talaga siya. There's a lot of statements for that, right? And then, so we don't tackle pa second law. And we will connect that later. Okay, maybe. Okay. And you will say, Sir Sotero, what about the third law? The third law is very specific also. It talks about perfectly crystalline solid. So, oh my gosh, that's solid, right? So we don't touch a little bit with that perfectly crystalline. Okay, so, okay, that's the ice cube, you know, that's perfectly crystalline siya. Okay, so it states there that the entropy change is always equal to 0. Okay, so never mind the third law, it's just, you know, it's like very theoretical, just like with the zero law of thermodynamics, very theoretical about thermal equilibrium. So let's focus on the first and second, because most of the topics will come out or in the examination is really the first and second law. Okay, like that. So Q is equals to, so change in internal energy class in chemistry, they are putting that as delta capital E. But then in physical chemistry, they are putting that delta capital U. So do not be confused, it's just only assigning a specific letter to identify. Okay, but it's not consistent, right? But never mind. Okay, let's understand na lang talaga siya that U and E is just the same in concept in this topic. Physical chemistry versus chemistry. Okay, like that. Okay? So that is, mag-delta U lang ta. Pero actually, it's also delta E. It's okay, but delta U because physical chemistry taron, di ba? So delta U. Okay? Delta U plus work. Okay, this is the first law of thermodynamics, right? Okay. Phase change ta ha. Let's forget a little bit of chemical reaction. Okay. This one. And then this Q, guys, is also known as the enthalpy. Okay? Because this is focusing in the heat energy. Okay? Heat energy content man good siya. So, automatically, Q is equals to delta H. So, delta H is equals to delta U plus W. Okay. What also triggered for some students or some engineers or, you know, in we study this specific subject because, you know, in the question or in the examination, okay, this will be used interchangeably. Okay, the Q and the delta H. And sometimes also, they are putting delta H. And then, some students, including me also, we are not aware pala na delta H is also MCPDT. You know that point? Because we said technically, Q is equals to delta H. And we are used to and familiar with the Q is equals to MCPDT or QMC delta T. So actually, we can use that also formula the same as delta H is equals to MCPDT. But since our instructors are not stressing that out, okay, for sure, because delta H are usually studied in physical chemistry. But during in our chemistry, I think this is only a suggestion to professors and instructors that we should also introduce that this delta H is always equal, so that in the minor, you know, minor level, or it's still in their lower level, the students can understand really that this delta H is equal pala with Q. Okay, so no need to think, because in this manner, it's good also in the part of the students, because it will lead the instructors and professors to exert the students an effort to really discover by their own. Okay, but it's more better also to specify during your discussion that in chemistry, that Q is equal to delta H automatically. Do not wait for the physical chemistry to be there in order for the students to understand that Q is equal to delta H. Because to be honest, delta H is usually discussed in physical chemistry naman talaga siya. It's not really a rigid discussion in chemistry. Because chemistry is just an overview. See, just right now, I'm sitting here, I discovered one new formula instantly, okay, on the spot. So delta H is equals to MCPDT pala siya, because we know that Q is equals to MCPDT. And technically, Q is equals to delta H. This is all about talking about heat content, right? So, oh my gosh, I discovered new formula by just sitting alone here instantly or on the spot. Oh my gosh. That's the interesting part of science, right? Okay, we can really discover something. Okay, see, since we know Q is equals to mcp dt, automatically it is also delta H is equals to mcp dt, because technically change of enthalpy or heat energy transferred is just the same with Q manggod siya. Okay, like this. Oh, nakakaloka. Okay, never mind. Okay, now we have Q is equal to delta U plus W, so delta H is equal to delta U plus W. Now, if we will substitute also this delta H with this equation, we can create also another formula. But never mind, another formula also that we are not used to. Okay, but because this is only now. Okay, maybe other discovered also already, maybe I am very late. No problem, but what I'm telling you, me just discovered now. Okay. Okay, now we will try to incorporate the enthalpy here for phase change measures enthalpy. So we will focus on equation number 3. Equation number 3. I have 3 equations here, right? So I will be focusing on equation number 2 because it is specific delta H, or the change of enthalpy of the formation of the substances. It could be either liquid, solid, or liquid here. Okay, now liquid evaporation. Okay, first process, evaporation. Ganon. Evaporation, okay, is a change phase from liquid to gaseous state, and it will produce a vapor. Okay, normally during the boiling point of a substance. When we mean of boiling point of a substance, there's an equilibrium of the pressure of the vapor and the pressure of the liquid surrounding liquid. If this is the container class, so if I have my glass, I will demonstrate to you, and I will put water. Actual demonstration so that you can understand what I'm talking to. Okay, this one. Okay, I will put water inside the glass. So, okay, this is the glass of water. This one. This is the glass of water. For example, this is already in the boiling stage. So the 100 degrees Celsius has been reached already. So that is boiling point. So when we mean of boiling point, technically, the pressure of the gas will escape. That pressure, okay, will be equal to the pressure of the liquid surrounding this liquid inside the glass. So if it will equalize in the equilibrium stage, so that is boiling point. It happens that the water will reach 100 degrees Celsius. But to other liquid substances or inorganic and organic substances, there's a possibility that it needs lesser than 100 degrees Celsius in order for them to boil, or having a very high boiling point compared to water. We don't know exactly unless we will do an actual experimentation in the laboratory, or we will be able to get a sample and put in a graduated cylinder, and then we will be able to boil it out to prove really if it is having a higher boiling point or a lower boiling point compared to the water, which is specifically 100 degrees Celsius is the boiling point. At that point in time, we need to have a comparative study and a comparative analysis just to prove if those substances have higher boiling point compared to water, and then at the time, we will have a graphical representation. We needed to graph that one to really compare and differentiate. Oh, it's gonna be like this. Water having lesser boiling point to ethanol. Ganun siya. So there's a lot of chemical substances na mabuang ta if you will try to do that all. Okay? That's why we need to illustrate only, and we need to give emphasis on water as our basis. Pure substance, liquid water. We cannot do that all. Maybe we can do, but for some. Okay? In our laboratory, if we're studying general chemistry, right? In the laboratory. Okay, there are two semesters in the laboratory. No, I think it's 2 semesters in the laboratory in the chemistry, general chemistry 1 and 2. Okay? And plus the laboratory in the physical chemistry also. It will be just keep repeating. Okay, but there's only an additional for some terminologies and some concepts, but still the basic foundation is already there. Okay, all you have to do is to intensify. Okay, intensify meaning to enhance. Okay, from the basic foundation, and we will add new learning topics. We need to add new terminologies, principles, and steps out of that. So it's gonna be like that. So evaporation, the boiling point there is very important. Okay, I'll put back the glass of water in my table. So, okay, and this is already the boiling point. Okay. So I will just pick the word here from this equation number 2. Okay. Here. Now class. So I need to illustrate spontaneous lang siya. Spontaneous meaning to say natural reaction lang of water. Not really that reaction, but phase change from liquid to water, okay? So I'll put H2O liquid, okay? H2O liquid to H2O vapor gas. Now I will ask you a question, class. If H2O liquid will change to H2O gas in a vapor state, right? This is evaporation process. Is this a reversible chemical reaction or a irreversible? Irreversible change of phase or reversible change of phase? It is a spontaneous change of phase or non-spontaneous change of phase? Take a look for this. And then cite an example if this can be reversed or not. And now, in that question, it leads you to think what is spontaneous, what is reversible chemical reaction. So this class, this is a reversible chemical reaction. This is spontaneous, something like that, okay? So that's why we have the term called steam, S-T-E-A-M, steam, okay? Especially in the pipeline, there's like a moisture or that goes out in the outer layer. That's steam. Okay, so meaning to say pala, it will goes back to liquid. That's just a little bit of moisture in liquid form, but not very large amount of moisture or liquid. But my point is, it will go back to being a liquid after the evaporation. So this is reversible chemical phase change reaction. So spontaneous. So H2O gas have an enthalpy change here, which is also negative in value. So in actual thinking and analysis, matched to the Fury, which is having also a delta H of negative value for water gas. See? So it will never be deviated from the concept of Fury if we try to put that in actual discussion. Okay, so it will goes back to liquid really. Okay, so a reversible chemical reaction and at the same time spontaneous reaction because the delta H is negative in the table presented here at 25 degrees Celsius, blah blah blah, so and so. Okay, ganon. Okay, now we need to use this second equation. Now, since spontaneous reaction or reversible chemical reaction, we don't add internal energy just to break down the bands of the reactant. Okay? Because H2O composed of hydrogen gas and oxygen gas, then we don't need extra energy just to break the band and the molecules compacted together in the liquid water. We don't need that one. Okay? Like that, something like that. So, we need to, from the second equation, we need to eliminate the delta U. So, we can already say directly, delta H is equals to W. Okay? So, delta H is equals to W. Okay? So, in evaporation, delta H is W because, as I said earlier, we don't need that energy at this moment in time, so it is automatically equal. So, meaning to say, the heat energy that is being released is completely used up to produce the work to the system in this mathematical representation. But if we convert that in a statement, theoretically, the change of enthalpy of the liquid water is completely used up to produce the work done of that water liquid to change into a vapor state. So in that alone, you can create your own definition if you really understand, not referring to the book already. Okay, you're using your own statement, you're using your own phrase. Okay, you memorize, but all of a sudden, if you understand, you can create your own definition. Okay, something, and you can create also your own terms to be inserted there. So that's the power already with English interpretation of a particular question. So they can really understand what's going on that said specific problem. So in this case, na-convert talaga siya all of the enthalpy, heat content of the water, okay, from liquid to vapor state. So delta H is equal to W. And now what is the formula of W? There's a lot of formula of W, if you can remember. Okay? There's a lot in physics and in chemistry. So what comes in your mind? Because we are dealing here with liquid to water. So you could not expect the work formula in terms of practical electricity, which is the Ohm's law. There's a lot of formula work there. And we can also apply the law of Bernoulli-Furey regarding the motion or the momentum versus impulse here. We cannot use that here because that is liquid to gas. So the last option we have is the work related to phase changes from liquid to solid. We will use that again from the ideal gas law equation, the PV in RT situation, in which the PV there is taken from the work in the first law again of thermodynamics. So work is equals to pressure times the change in volume. Okay, something like that. We will use that here. So delta H is equals to pressure times the change in volume. Ganon. Now interpret that one. Let's have that interpretation. Okay, change in enthalpy is equals to the pressure times change in volume. So again, we can create another formula also in this on the spot. So we can also say Q is equals to pressure times the change in volume because technically Q and enthalpy is equal man siya. Okay, on the spot, we can create another formula of heat which is Q is equals to P times change in volume. Oh my goodness, really? Okay, 4. Question number 4. Okay. The equation number 4 is Q is equals to pressure times change in volume. Okay, class. If we don't put a sine triangle as a change, right? So that means there will be a constant pressure all throughout on the process. There's no initial value of the pressure, there's no final value of the pressure. That's what we mean of not putting delta or triangle. If we put delta like this, that's a change, meaning there's initial stage and final stage. So you should be careful for that also during the substitution or during the problem. See, if the problem is specifying only a constant pressure all throughout the problem, then this will be applied. But if the problem are stating 2 pressures, 3 pressures, this will not be applied anymore. This WC, delta V, or else you will try to put another W1, W2 separately, pressure 1, pressure 2 times delta V, something like that. But it's also rare for that. Okay. So you will be opted to use another formula already that undergoes pressure 1, pressure 2. What are those? So those are the Boyle's law, like, right? P1 V1 equals to P2 V2, something like that. Or you can have the Dalton's law of partial pressure, if you can remember. Okay? The sum of all pressure or the total pressure is equal to the sum of its partial pressure of the component. Something like that. That is Dalton's law of partial pressure, because there's a lot of pressures given there. So this equation here is only limited at one pressure given in the problem. But there's 2 volume given in the problem, because there's a change in volume. Okay, so in that manner we can really understand, okay, that the delta V here undergoes a change in a state function, final and initial, like that. Okay, so P delta V. Okay, ganon siya. Okay, this one. Okay. Since we are talking here as a reversible chemical reaction, so we can say, class, that vaporization, right? So we can just have latent heat of vaporization is equal to the work done on the system. Okay? Work done. Take the term on or to. Because if you use by, that's negative work man siya. But in here, is delta H is equal to W man siya. There's no sign, negative sign man siya. So you will be stating this in a statement that, okay, the latent heat of vaporization, which is equal to the enthalpy change of the liquid, okay, is equal to the latent heat of vaporization when it is in state of the gas. Okay, or it is equal to the work done on the system or to the system when it changed already to vapor. Okay, because work done by the system is negative bias, so be careful. So just work done on the system or work done to the system. Okay, you get the point? Something like that. So I will show now latent heat of vaporization, or you can simply use also as heat of vaporization lang siya. It's technically the same, but some books man good are using latent, and some students also will be confused, what's this latent all about? But it's the same, putting it or not putting it, it's just the same. Okay, we can just only say heat of vaporization. Ganon. So that means enthalpy of vaporization. That's also the same, because we're referring only all to heat. Okay, it doesn't matter at all. Okay, so heat of vaporization, enthalpy of vaporization, latent heat of vaporization. Okay, like enthalpy change of vaporization. So the clue there is the heat, and there's a change involved there. Okay, okay, we don't have to put word for word for that. Okay, as long as you can understand really that it refers to heat. Okay, something like that. Okay, so latent heat of vaporization is just equal to heat of vaporization, or also equal to enthalpy of vaporization, or equal also to enthalpy change of vaporization, or equal also to heat change of vaporization. But you will never usually use the change word in the problem solving. Never mind, but we are referring the same. Okay? Like, I am very particular with the phrasing, how it will be phrased in putting that in the problem, so that you can understand really what's going on in the problem. Okay, because it helps us to understand easily and to interpret easily, okay, the terms the words incorporated in the question. Something like that, okay? So, going back. So, latent heat of vaporization. Charot. Talaga. Talaga mahurot yun akong pentel. Latent heat of vaporization. Okay. Since we are considering this as a reversible chemical reaction, we don't need to use the internal energy, okay? Is equals to... But if we need to use that, it's also possible naman talaga siya. So, we should also use that somewhere along in our discussion. Okay? But I'm trying to point out naturally pa, walang mga additional, whatever. Okay? So, it exists naturally, something like that. Okay? Okay, something like that. For example, guys, so what I can say is that if we put liquid inside the glass and you put that in the ground and there's a sunlight, okay, sun is UN. So the liquid will become lesser after 2 hours and 3 hours because the liquid water is very volatile. You know, volatility matters there. The characteristic of volatility will matters for liquid. So the characteristic and the ability of the liquid to change that into vapor, how quick and how fast is known as volatility. Okay? So even though we don't heat that, but there's the presence naturally of the heat of the sun. So that's why the volume of the liquid water will become less through natural process. That's why this is reversible chemical reaction really. Okay? The liquid water to gas. We don't put anything artificially manggod. Okay? Meaning, no person there to make it less the volume of the liquid. Okay? If we just stand there, it will just automatically do the job in evaporating the water to vapor. Like that. That's what we mean of reversible chemical reaction. Okay? But if we put something there, nag-effort ta, ato siyang gipot ang mga something there, catalyst or whatever, i-adjust na to ang temperature, and then just to change that to another change. So that is a reversible chemical reaction. So you add more energies in that system to change the phase, something like that. So that's the logic there, okay? The logic of reversible and irreversible chemical reaction, or reversible or irreversible process. So in my discussion here, we are referring to reversible process. Okay? So, latent to the vaporization is equal to the pressure. So, the pressure here, class, is the pressure of the entire system. Okay? The pressure received by the vapor and the pressure received by the water. That's why we have only one pressure there. There's no change in pressure. The change in pressure is not the focus. Okay? Like this. So, this is the pressure of the system. So what's in the system is the water, right? The hydrogen gas and the oxygen, okay? And the vapor. Because originally the vapor, before it will go to the atmosphere, it will stick first to liquid. So they are receiving equal temperature, they are receiving equal pressure also at the same time. Am I correct? And after that, it will evaporate to the atmosphere. Okay? The molecules of the vapor. But first, it will stick first on the surface of the water, technically. So that's why we are using the same pressure lang talaga siya, pressure of the liquid water and pressure of the water. That's why in our formula, work is equals to P times change in volume. There's only P there, not delta change. Okay? Like that. Now for the volume, we have this is now the volume of the gas vapor minus the volume when it is still a liquid. Okay? That's why delta change of the volume. Or we can say already that final volume and initial volume. What we mean there, that the final volume took place already the change phase to vapor. Okay? And the initial volume is the volume originally of the liquid water that doesn't change the phase. Okay? There's no process took place yet. So that we can really agree in this topic of change, enthalpy change phase, change of phase. Okay? So, delta V. Ganon. Okay? So that is, or we can state that one as V2 minus V1 in algebra. But for me, I don't like that much because number doesn't signify at all. Number 2, 1, 3. I want F and I. This is very easy to understand in English that F is the final. And in the final, it became vapor. It became gas. And initially, it is a liquid. Something like that. So it's very easy to understand by putting F and I in the subscript compared by putting 2 and 1. You get the point? Because most of the times also in solving problems, V2 minus V1, P1 minus P2, but I would rather put PF, PI, VF, VI because it's easily understandable. F is final stage, I is initial stage, which is more accurate compared to having a subscript of 1 and 2. Okay, but it doesn't matter. We can also get the same answer. But what I am referring, the most precise of putting the subscript is really the F and I, not the 1 and 2. But it will just yield the same answer, no problem at all. Okay, what I'm trying to emphasize, we will also use the subscript that is more closer to reality. Okay, closer to reality. Okay, because in reality there's no number there. Okay, when I boil the water, there's number 1, there's number 2. Nothing. It's always final and initial step. The initial step, I will put the water inside the kettle. The final step, it will vaporize. So it's gonna be F and I supposedly, you will be used in the subscript, not the 2 and 1. Okay? But it's just the same, no problem. Okay, it's up to us. Where is our comfort zone? Okay, or what are the things that we are used to? Because in Boyle's law also, that is P1, V1 is equals P2, V2. It's not PF raba. It's not raba PI, VI, and VF, VF. And we are not used to also in using that one also. It depends on the situation, Okay, but what I'm trying to say, the real putting on subscript supposedly will be based closer to reality. Okay? Like that. So it should be VF minus VI rather than V2 minus V1. Okay? Because if we have also, for example, if I have a lot of phase changes, 4 changes or 3 changes, for example, it is solid, it will become a liquid, it will become a gas, and a body, it will become liquid. Don't you think you will use 1, 2, 3, and 4? It will be more confusing. Okay, so you will use already the final and the initial, which is the number 4 and the number 1. Because in this topic also, each reaction phase change will not matter at all. Because enthalpy is a state function. It doesn't depend on the path it covered. It's really basing on the final and initial stages at all. Even though 2,000 times it has a reaction there in each reaction step, the most important is the final and the initial. Okay, like that. So it is also very closer to use F and I only, not the number 1, 2, 3, 4, 5, 6, 7, 8. Because there's also situations a lot of changes will be taking place. Okay, in somewhere in your chemical reaction. Again, it will go back to solid, again liquid, solid, liquid. So how can you do that if you are referring only to number? Okay? So you will say volume 1, volume 2, volume 3, volume 4, volume 5, volume 6, volume 8, volume 9, volume 10, until volume 2000. Okay, something like that. So it will really confuse also the declaration of the subscription. Better use only initial and final class, VF and VI. Anyway, enthalpy change is a state function. Okay? Even though how many reaction steps, we will be basing to the final step and the initial step. Okay? That's very clear. Okay, now VF minus VI. Okay? Oh my gosh. So this is the volume of the vapor and the volume of the liquid, to make it straightforward. Right? This one. Now we can say, since delta H is equals to W and W is equals to pressure times the delta change in the volume, so we can say latent heat of vaporization is equals to the pressure times the final volume of the vapor minus the initial volume of the liquid. Okay? So gonna state like that. So that is latent of vaporization. That is the first, evaporation. Now we take also the constant here. Okay, the value of constant, so that we will be satisfied in using that in our equation. So we have, wait, wala na chukoy pintil class. Charot. Okay, no, purot yun siya o mga suwat, whatever. Okay, so we need to determine the value for this.
The Bluetooth device is ready to pair.
What's happening? Oh my gosh. Wait! Nahuman na ta sa evaporation. Let's have 4 processes. Oh, 5, I think so. Oh my god, time check. Let's go to powdered Alaska milk. 96.3 W rock. Naman. Talaga. Oh my god. Grabe. Okay. Okay, class. Charot. Oh my god, uy, no. Nahurot siya Enthalpy. Wait for a while ha. Atong tiwason ang let's finish latent to vaporization and we will do in the next vlog on live stream regarding sublimation, like blah blah blah, deposition, condensation, like that fusion. Okay, so that we can really understand phase changes is very important also in studying physical and chemical principles coverage. Ha! Be careful so that you will attain a very high score in your physical and chemical principles coverage. Okay, if you will be taking your board examination. Ganon! Build with theories and concepts first before problem solving. Okay? Gosh. Hello guys! Oh, dapat na dyan mahurot. In fairness. Somebody said also to me, Sir Sotero, what if I'm not fan, FUN, I'm not fun with memorization? And then, if you really like to take this course, or course related to science, specifically pure sciences, there's a lot, right? I don't have to mention. Related to science, biology, chemistry, physics, chemical engineering, pharmacy, like that. BS Pharmacy, a lot of chemistry will be there. Okay? BS Pharmacy, BS Forensic Science, BS Biotechnology, BS Nuclear Engineering, something like that, BS Physics, BS Chemistry, BS Chemical Engineering, BS Biochemistry. Those are sciences courses. Then if you don't love to memorize, then better decide na. Okay? Because a lot really of memorization in this type of courses. Okay? And if you love really purely mathematics, then take a course that is not related to science. For example, mechanical engineering, electrical engineering. It's related a bit with science, but not purely with science. So you use ECE, civil engineering, okay, sanitary engineering, something like that. But if you think you will take related sciences, engineering courses, or sciences, then better decide now if you don't love memorization. Okay, say this to you frankly, really. Okay, if you don't love memorization, better not to take this kind of course, because in the problem solving, you also have to memorize the way it is being carried out, how to solve. That's why you need to have practice problem solving, because the attack and the method of the problems, you will also memorize that. Maybe it will come out again, so I will use the same method in that particular problem. So still you are memorizing. Okay, the way how it's being solved. Okay, so that means if you don't have adequate memorization and thorough memorization, even though you like that, then you will force yourself to memorize. There's no question about that. But if you don't really love to memorize sciences, then better take another course. Okay, if you love numbers that much specifically, then go to BS Accountancy, something like that. Or you love money, then go to BS Administration, Finance, Banking and Finance, or other college arts and sciences courses, psychology, or political science. If you love verbal speaking and analogy and comprehension in reasoning, logical reasoning and verbal ability reasoning, then go to political science. Okay, it doesn't need really pure sciences to do that. Okay, but my point is, if you really love to take related sciences courses I mentioned now, better adopt the culture and habit of adequate and thorough memorization. Okay? Deal? So that's the deal now. Okay, we'll go back to... I will take my coffee first. So I'm telling you guys, okay, I'm telling you guys, I'm not good in mathematics, right? I'm not good in mathematics. I don't have a very high IQ in mathematical ability. But then why I became a registered chemical engineer? Supposedly I will not pass. But why? Because I develop on theories, concepts, principles, and memorization. Okay? It's very easy to analyze if you remember and retain in your brain cells those principles and concepts and theories, and then problem solving will just follow. Okay? Because you understand really the basic foundation. Okay, though you will find difficulty because you are not really a mathematics lover, but you can easily develop that somewhere along the way. Okay? Especially if you adopt too much effort and study moment somewhere along in your first year college to fifth year college, then it can be developed. Okay? So never be afraid if you are not good in mathematics, then you love really to become an engineer. You can still follow your dream to do that. But please do a lot of memorization. Okay? Oh, wala ako tubig. Mag-evaporation pa class ha. I will put water in the kettle and let's do the evaporation process. And 100 degrees Celsius boiling point, this liquid will boil and will change into the vapor state. And we can apply the formula of latent heat of vaporization, which is equal to the pressures of the change in volume. Okay, like that. With a while, I will be able to have coffee transfer during making my coffee. Charot! Ganon! Grabe naman. Talaga? Yes. Mag-coffee sa tao, eh. Ako rin tiwasan ang latent heat of vaporization, ha? Then second, condensation. Latent heat of condensation. Oh my gosh. So while waiting for the liquid to boil, so I must continue. Okay talaga. Okay. Paano na to? So, latent heat vaporization, this is the formula, right? Now, we need to memorize what is the latent heat vaporization value of water at 100 degrees Celsius.
The Bluetooth device is connected successfully.
Guys, this is a topic of latent heat of vaporization. So what is the value of latent heat of vaporization of water at 100 degrees Celsius? So that is 2,260 kilojoules per kilogram. Okay, have a sheet of paper and memorize. Okay, especially if you are now facing the board examination this coming October, or chemical engineering graduates there who are taking the review. Okay, memorize this. 2,260 kilojoules per kilogram is the latent heat of vaporization of water at 100 degrees Celsius. Again, write it down in a piece of paper. 2,260 kilojoules per kilogram is the standard value of latent heat of vaporization of water at 100 degrees Celsius. Okay. Another value, we have 40.8 kilojoules per mole. And take note, guys, the denominator is mole, 40.8 kilojoules per mole. So this is the molar latent heat of vaporization of water at 100 degrees Celsius. Now, why I introduced this to you? Because sometimes it will never be given in the question. We'll just say, what is the enthalpy change of water at 10 degrees Celsius? Just like that. No other thing. And then you will be panicked. What's the formula of water? Q is equals to mc p dt. And you need a lot of quantities. Sure. No, it's not like that. You can automatically get the vapor pressure and then multiply. Kalas, bingo. You can get already the enthalpy change of water at 4 degrees Celsius. Okay, because the water has its enthalpy formation value. Then multiply that immediately with 2260, then kalas, you already have the heat. Do not go with their work is equal to NR times T, PV and RT, then like that, Q squared and too much quantities you need for that. So here it's very easy of question in the theory. Okay, in the physical and chemical principles. Very quick. Okay, sometimes 1 sentence, 2 sentence, 3 sentence. Okay, like that. It's very easy really, okay? But our minds only are thinking difficult, but it's very easy to solve. Okay, like that. Okay, memorize. So, 2,260 kilojoules per kilogram is the latent heat of vaporization of water at 100 degrees Celsius, and the molar latent heat of vaporization of water at 100 degrees Celsius is 40.8 kilojoules per mole. Ganon siya. Okay, now if you try to convert that one, then it can be easily converted because I advise you also to memorize the conversion factors, the most joules, then you can have the calorie also. But me, I memorize really so that I don't have time to convert. So in calorie per gram, that is 530. 530 calorie per gram is the latent heat of vaporization of water. So actually, if you convert this to 2,260 kilos, so that if the question will have a calorie unit, then I can put directly that there, saving my time. I can proceed to other questions easily. You need to convert. Okay, something like that. But the only wrong there, if my memory fades. Okay? But there's choices there. A, B, C, D. If the choices is having an exact in the choice, then I have to choose that's correct. Okay? But in first place, I memorize the value of the latent vaporization. So it saved my time, really, and I'll go to another question. Number 2, number 3, number 4, number 5. It really helps if you really memorize the most basic constant values in science. Okay? Like that. So that is all about latent heat of vaporization. And then later we'll be going back to latent heat of condensation later. This I'm very lengthy already. This is very lengthy already. Thank you so much for watching this live stream. Down the line.